Right, guys, we are going on to page 198, 5.4 atomic electron energies. So what I'm going to start off with is defining something called the electron volt. It's a convenient unit of energy, especially in quantum physics and particle physics. The definition, something you will need to know. It is the amount of energy gained by an electron as it accelerates through a potential difference of 1 volt. Now, how do we arrive at 1 electron volt equating to 1.6 times 10 to the minus 19 joules? Now, we know that the volt is defined as the work done per unit charge. Rearranging that gives us the work done is equal to the potential difference times by the charge. Now, considering that we are accelerating an electron, often the notation that we use for the charge of an electron is the letter E. So rather than write down Q, we write E. Now that E represents the charge in coulombs of an electron. And rather than write VE, we write E times by V. So the charge on an electron multiplied by the potential difference that electron has been accelerated by gives us the work done on that charge. So if we use that expression of work done is equal to the charge on the electron times by the voltage, that gives us the work done in joules. So this is volts, this is coulombs, and we get an answer of joules. So what's the charge on an electron? That's 1.6 times 10 to the minus 19 coulombs. And when it is accelerated through a potential difference of 1 volt, then the potential difference is 1, and the work done on an electron accelerated through a potential difference of 1 volt equals 1.6 times 10 to the minus 19 joules. So 1 electron volt is equivalent to 1.6 times 10 to the minus 19 joules. Whenever we are performing a calculation, we must use joules. And often in quantum physics and particle physics, the questions will be written in electron volts. So it's important to remember to convert into joules when performing calculations. So what we've got as an example here is cathode ray tubes, such as the one used by Thomson, achieved electron energies around about 1 kilo electron volts. The LHC, the particle accelerator in Geneva, can accelerate protons, charge carriers, to energies in terms of tera electron volts. So this is 1900s, more than 100 years ago, and this is now more recent. So we've been able to create very large accelerating potential different accelerating energies going from 1 kilo electron volt to 1 tera electron volts. No, now I'm using energy in electron volts rather than in joules, and that is a more convenient unit in topics such as quantum physics and particle physics. So the next statement I want to focus on is when an electron is passed through a vapor of an element, the electrons collide with the element of the vapor and light is given off. So an example of this will be, let's say, a vapor of hydrogen gas, and an electron is passed through the vapor. The electrons then collide with the element hydrogen and the electrons within hydrogen, and as a result, something is produced called the line spectra. That light that is given off from the vapor is passed through a diffraction grating, and we know all about diffraction gratings. It spreads out light, and we produce something called the line spectra. So by pictures, what's that showing? So we've got electrons accelerating towards a vapor of hydrogen, and light is given off that we pass through a diffraction grating. The light then diffracts outwards, and on a screen, observing this diffracted light, we will see the n equals 0 order, the n equals 1 order, the n equals 2 order, and so on, depending on the incoming wavelength. Often, as we know from our work in waves, the n equals 2, there's quite a lot of overlap between the orders. N equals 0, we don't see all the wavelengths arrive at the same point, so we won't see separation. Often what we use is we look at n equals 1, and what we see in the n equals 1, and remember that with diffraction, blue light for the n equals 1 will end up, let's say, if we're looking at this region here, so let's say the blue light will end up there, the red light for the first order will end up maybe further out, somewhere, let's say there. So all the other colors will appear in between these points here, and that's your n equals 1 order for blue, and all the colors in between up to red. Now, this here, we have a single electrons interacting with the inside of the hydrogen, and as a result, we get light being produced. Not unfortunately, what we have is light that which is produced is not the continuous spectrum. So we do not have all the wavelengths from blue all the way up to red. So we only have specific wavelengths given off. And if we look, the n equals 1 order on the screen will appear like that. So we don't have all of the colors. We've just got a line here, a line here, a line here, and a line here. Now, We know that is a line corresponding to a specific wavelength, and that a different one, that a different one, and that a different one. Now, from our physics that we have done, we know n lambda equals d sine theta when waves pass through diffraction grating and interfere. This is for all the constructive interference of light. Now, if we have the n equals 1 order, so we know that, so that's 1 for all of these. We know the distance between our slits, so we know that distance there. We know the angle from the horizontal for each line where it appears on the screen relative to the horizontal. So we know these angles. And from there, what we could do is work out the wavelength corresponding to each line. And underneath this emission spectra or line spectra, this is specifically for hydrogen, we see a set of unique lines. It's like a barcode. It's very specific to hydrogen. This is the line spectra for hydrogen everywhere in the universe. Not just specific to a lab or a point in space. It's unique to the element. Now, the reason why I'm discussing this, it's because there is a direct link between line spectra and the position where the electrons are inside an atom. So here are more line spectra, but for, let's say, a different element. Now here you see many lines. It's a black and white picture. Different element, different set of wavelengths. It's like a barcode for a different element. So let's start off. Rutherford's model of the hydrogen atom has one electron orbiting a very small, dense, positively charged nucleus. So when Rutherford did his experiment, he said that you had a positive center and these electrons whizzing around on the outside. Now, with hydrogen, you only have one electron whizzing around the outside. But this model, there were problems associated with what came next. Because in classical physics, electrons are negative, the positive center, there should be a force of attraction. And any electron that is moving in a circular path, it's continuously changing direction, so it's changing its velocity, therefore it's changing its acceleration. So it's accelerating when it's in orbit, and any charged object that is accelerating in classical physics emits radiation. So all charged particles emit radiation when they accelerate. The orbiting electron is accelerating towards the center, and it's constantly changing direction. According to laws of classical physics, the electron should radiate energy all the time. Unfortunately, we do not pick up any of that radiation, so classical physics pose cannot be used to describe what's happening inside the atom. This is where the birth of quantum physics